If you could see outside my window today, you would see a lot of snow, and you would see snow plows going by, scraping the snow off the road so the cars can get through. You would also see them dropping salt on the road, usually a mixture of salt and sand to provide some extra traction, but salt in order to melt the snow and the ice that is present on the road. Why do we use salt on roads in the wintertime to melt the ice? Well, the reason is because adding that salt actually lowers the freezing point. So instead of it melting at 0 degrees Celsius or 32 degrees Fahrenheit, it's going to melt at a lower temperature so that we can actually get the snow melted and the cars will be able to get through a little bit easier. Why does that work? Well, in order to get something to freeze, when something freezes, what basically happens is you've taken enough energy away from the molecule so that they stop moving around all over the place and they kind of settle down next to each other and they're just vibrating. And so in order to take that energy away, you're going to drop the temperature. If you've got ions present in solution, we talked one of the very early videos, very first one of the chapter, how the attractive forces between the ions and the water cause the water molecules to surround the ions. So those attractive forces are going to draw them together. So that actually almost produces some extra energy in the solution. And so you've got to drop the temperature that much more to take that energy out of solution and to get the solution to actually freeze. So that is why we put salt on the roads in order to drop the temperature, is because by dropping the freezing point, the snow and the ice will melt at a lower temperature than it would normally melt at. Okay. The first sample problem that I gave you says if I have solutions of sodium nitrate, magnesium nitrate, and aluminum nitrate, and they all have the same molality, which one of those will lower the freezing point the most? Does it make a difference? It does make a difference, actually. If you remember, again, earlier in the chapter, we were talking about how many ions these would break down into. When I put this into solution, this sodium nitrate will break down into a sodium ion and a nitrate ion, which would be 2 ions that this breaks down into. The magnesium nitrate will break down into a magnesium ion and 2 nitrate ions, which is a total of 3 ions. Where the aluminum nitrate will break down into an aluminum ion and 3 nitrate ions, which makes a total of 4 ions. So all else being equal, the aluminum nitrate is going to lower the temperature, lower the freezing point more, because there's more ions to get in the way, more ions to cause attractive forces, to cause the water molecules to want to surround them, so the more energy I have to take away. So the more ions you have in solution, the more you're going to lower your freezing point. Well, exactly how far can you lower the freezing point? This actually brings up an interesting concept, because in recent years, the highway departments, instead of using sodium chloride, started using calcium chloride instead. And if you think about the formulas for that, NaCl, the sodium chloride that they used to put on the road, will only put 2 ions into solution. They started using calcium chloride, which puts 3 ions into solution, so they can use the same amount, but this will actually lower the freezing point more, which is helpful when you've got an air temperature down around 27, 28 degrees Fahrenheit. It makes it much easier then to get that snow and ice melted on the road so that you don't have so many accidents. So in order to figure out exactly how far we're going to lower the freezing point, we're going to use this equation, delta T, and the delta stands for change. So I have the change in temperature is equal to a negative, and you have to make sure you get that negative in there, I, and the I is for how many ions does the solute put into solution, times the K sub F, the constant for that particular solvent, times the molality of the solution, okay? Now, what you want to watch is that this is going to give me the change in temperature. It does not give me the new freezing point. It just gives me how much the temperature is going to drop. For water, it doesn't make quite as much of a difference, but we're going to work 2 problems today where you'll see that you have to watch that and not just assume that once you work the problem that that's your final answer. So let's look at the first problem on your sheet here. What will the freezing point be of a solution made of 15 grams of NaCl and 100 grams of water? And it says the Kf of water is 1.86 degrees Celsius per molal. Well, if I'm going to use this formula, I have to know the molality, and they didn't give me that. So the first thing I've got to do is calculate the molality of the solution. I know that I have 15 grams of salt, and so I need to convert that to moles. In 1 mole of salt, there are 58.44 grams of salt, and so grams will cancel out, and that will give me 0.257 moles. Again, this is molality of the solution, and molality is the number of moles over the number of kilograms. So I've got 0.257 moles. It says that I have 100 grams of water. If I take that decimal point, move it 3 places to the left, that's going to give me 0.1000 kilograms. And so when I divide that out, it's going to be 2.57 molal for my solution. Okay, now I have enough information that I can use this equation. So the delta T is negative, what's I? Well, I have an NaCl solution, which was this one right here, and I said that's going to give me 2 ions when it ionizes, when you put it into solution. So for NaCl, the I is 2. The K sub F, the problem tells me it's 1.86 degrees Celsius per molal, and the molality I just calculated is 2.57. Okay, so when you multiply that out, the molalities cancel out and you're left with degrees Celsius. So the change in temperature is a negative 9.56 degrees Celsius. Now, because this is dissolved in water, the normal freezing point of water is 0. So what that means is that my new freezing point is going to be 0. It's going to drop 9.56 degrees Celsius. So my new freezing point is a negative 9.56 degrees Celsius. Okay. Now again, for water, this and this turn out to be the same thing because the freezing point is 0. It doesn't turn out to be the same thing if your solution is made with something other than water. So let me make some more space here. And the second problem that we do will show you what you're going to have to do if that is not the case. Alrighty, so our second problem says, what will the freezing point be of a solution made of 0.394 moles of magnesium hydroxide and 25 grams of acetic acid? So I've not made this solution in water, I've made it in something different. It gives us the freezing point of acetic acid to be 16.6 degrees Celsius, and you'll notice that the Kf is different as well. So this time we're not given grams, we already have moles, so we can calculate molality by taking the number of moles, which was 0.0394 moles, and I'm going to divide that by the number of kilograms. It was 25 grams, take that, move the decimal point 3 places to the left, so it's going to be 0.0250 kilograms, and so when I divide that, I have 1.58 molal solution. Okay, now I can use this equation. So my delta T is going to be, now it says that I've got magnesium hydroxide. So what's the I for that? Well, magnesium hydroxide is going to make 1 magnesium and 2 hydroxides for a total of 3. So I'm going to have a negative 3, as that was here. The Kf, it tells me, is 3.90 degrees Celsius per molal. And then I have 1.58 molal that I calculated from up here. Okay, so the change in temperature, when I multiply this out, gives me a negative 18.5 degrees Celsius. However, We're not talking about water. We're talking about acetic acid. Okay, so in this case, I've got to figure out what my new freezing point is. So my new freezing point is, I'm going to take the original freezing point, which was 16.6 degrees Celsius. It's going to drop 18.5 degrees Celsius. And so therefore, when I do that subtraction, my new freezing point is going to be a negative 1.9 degrees Celsius. That's supposed to be a C. Okay, so if you have water, again, like I said, this answer is going to be the same as the new freezing point. If you don't have water, you're going to have to do an additional step and do this subtraction to figure out what the new freezing point is going to be. You will also notice, I'm going to go ahead and throw this in there. We're going to do freezing point today. We're doing boiling point tomorrow or in a couple of days whenever you do the next section. Boiling point goes up for the same type of reasons that we've talked about for the freezing point going down. So with boiling point, you don't have to worry about this negative sign. The negative sign's not there. So I just wanted to point out that difference to you so that when you see it tomorrow or the next day, when you do the next section, that won't confuse you. Because freezing point drops, so therefore you need a negative sign. Boiling point rises, and so therefore that's going to be a positive sign when you do those types of problems, and they are done exactly the same way as these.